What do a trick played by a grocery store cereal box and a life-saving IV drip in a hospital have in common?
On the surface, absolutely nothing.
Right, nothing at all. But underneath, they both actually hinge on mastering one foundational and honestly often completely misunderstood mathematical concept, and that is the unit rate.
It really is everywhere.
Welcome to today's deep dive, where we are looking at the math of per unit values. Today, we're pulling from a pretty diverse stack of sources. We've got nursing exam prep books for the TEAS and HESI, historical scientific journals, and even some cognitive psychology research.
Which is quite the mix.
Yeah, it is. For anyone out there prepping for those medical exams, or if you're just trying to be a sharper thinker and a more defensive consumer, our mission today is to break down exactly how to compute, compare, and truly understand rates. We are going to move way past those basic mathematical assumptions we all carry around.
And, while finding a unit rate might sound to you like simple division, like just punching a numerator and a denominator into a calculator, the reality of how this math functions in the real world is far more profound.
Oh, absolutely.
I mean, this specific mathematical idea has sparked historical scientific breakthroughs. It forced the creation of modern consumer protection laws. And, believe it or not, it continues to ignite fierce debates among math educators and psychologists today.
Debates about how our brains even process numbers.
Exactly.
Okay, let's unpack this. Because before we can use rates to defend ourselves in the real world, we have to define what they actually are, and maybe more importantly, what they aren't.
That's a great place to start.
I want to start with the first major fault line in math education that our sources highlight, and that's the difference between a ratio and a rate. Because honestly, I always thought they were basically the same exact thing.
A lot of people do. It's a very common misconception.
Right. To me, a ratio is comparing apples to apples, like comparing 3 red marbles to 5 blue marbles.
Yeah.
But a rate that is comparing apples to hours or apples to dollars, why have textbooks historically blurred this line so much?
Well, that blurring of the line is exactly what gets people into trouble, especially when they reach higher level sciences. A ratio, like your marble example, compares two quantities that share the exact same unit.
Right, you're comparing marbles to marbles.
Exactly. Because those units match, they effectively cancel each other out in the math. Think about it algebraically. If you put marbles over marbles, the word just disappears. The ratio 3 to 5 is a pure unitless number.
Got it.
A rate, however, compares two quantities measured in entirely different units, like 60 miles in 1 hour, for example. The critical distinction is that in a rate, the units never cancel out. They stay attached to the answer forever.
So it's always miles per hour.
Always.
So a rate is completely naked without its units.
It is entirely meaningless without them. But for a long time, loose historical usage in textbooks meant any fraction comparing two things was just lazily called a ratio.
Which sounds like a recipe for disaster.
It is. Treating them as the same thing leads to massive errors, especially later on in physics and healthcare. The U.S. Common Core Math Standards, which were finalized back in 2010, they deliberately intervened to tighten this vocabulary.
Oh, really?
Yeah. They defined a rate strictly as a units per 1 unit of B. They wanted to stop students from treating 60 miles per hour and a 3 to 5 ratio of marbles as the same kind of mathematical object.
Because physically, they behave completely differently.
Precisely.
That makes perfect sense. You can't just drop the words miles and hours and expect the math to still work in the physical world.
Yeah.
And that brings us to the unit rate, which is a special case of a rate where the second quantity, the denominator, is reduced to exactly 1.
Right, the per 1 value.
Yeah. So instead of saying you drove 120 miles or hours, the unit rate tells you that you drove 60 miles per 1 hour.
And that per 1 reduction is crucial. But it introduces a secondary trap that catches a lot of people. People naturally assume a unit rate is constant.
What do you mean?
Well, in everyday speech, you might tell a friend your car's rate of speed was 60 miles per hour. But we know you sped up on the highway, you slowed down for traffic, you stopped for a red light.
Right. I wasn't frozen at a rigid 60 miles per hour for the entire trip.
Exactly. That 60 miles per hour is really an average rate. It mathematically masks all that instantaneous moment-to-moment variation.
Oh, wow. I never really thought about it like that.
Physicists, and later the field of calculus, had to formalize this difference. A constant rate is one steady number that never wavers. An instantaneous rate, the exact speed of your car at one specific millisecond in time, can be entirely different from your average rate over the whole trip.
That's a huge distinction.
It is. Now, in nursing and health science math, You are almost always working with constant or average rates, things like milliliters per hour or breaths per minute, but it is vital to remember that an average rate is not a guarantee of what is happening at every single moment.
Okay, so speaking of physicists, I know the sources trace this idea back to Galileo somehow. But what was he actually doing with unit rates? How did we go from not having this concept to, like, using it to measure the universe?
Well, the etymology in our sources traces the word rate back to the Anglo-French word rate, which comes from the medieval Latin rotipars.
Rotipars, meaning reckon part, right?
Yeah. It was originally tied to a verb meaning to reckon or calculate. By the 14th and 15th centuries in English commerce, the word rate already meant a fixed proportional charge.
Like banking terms.
Exactly. You had the rate of exchange or the rate of interest in banking long before it ever entered a mathematics classroom or a science lab.
But then Galileo steps in, and he is under house arrest in 1638, right?
Yes. Galileo was confined by the Inquisition, and he used that time to write a groundbreaking book. He was rolling balls down inclined planes and timing them with water clocks.
Water clocks, that's amazing.
By doing this, he became one of the very first to rigorously define speed as the ratio of distance traveled to time elapsed.
Which sounds completely normal to us now. I mean, we see speed limits every day.
But it was a monumental paradigm shift back then. Before Galileo, motion was described in qualitative Aristotelian terms. People didn't use numbers to describe falling objects. They just said, heavy things naturally fall faster.
Oh, so they just kind of vibed it.
Pretty much. Galileo insisted on expressing motion as a measurable rate, distance per unit time. This is widely cited as a founding moment of mathematical physics.
It's wild to think that a math concept used by Galileo to invent physics eventually became consumer protection law.
It really is quite a leap.
Because fast forward a few centuries to the mid-20th century United States, and grocery packaging was essentially tricking people. But if consumer laws rely on shoppers actually doing this math in the aisle, how did that transition happen?
It started out of absolute necessity. By the 1960s, grocery packaging had exploded into dozens of different, highly confusing sizes.
Like economy size, family size, jumbo size.
Exactly. It made price comparison nearly impossible to do just by looking at the boxes on the shelf.
I mean, it was too computationally heavy for everyday shoppers to compare a 14-ounce box to a 22-ounce box just by eyeing it.
Right. So Esther Peterson steps in. She was Lyndon Johnson's special assistant for consumer affairs in 1964.
She led the charge, didn't she?
She did. Peterson pushed retailers and legislators to require tags that posted the price per standard unit. So price per ounce, price per pound, per 100 sheets of paper towels.
That's brilliant.
Some large supermarket chains actually started doing it voluntarily to win consumer trust. And by the 1970s, many states and cities had passed mandatory unit pricing laws.
I find that incredible. A mathematical idea was literally legislated into consumer protection law to stop people from getting ripped off. So knowledge really is self-defense here.
Absolutely.
But if the law gives us the numbers, how are we supposed to compute and compare them on the fly? Let's actually walk through the mechanics.
Sure. It all comes down to 4 first principle steps. Step 1, identify the 2 quantities being compared and their units. Remember, to have a rate, you need 2 different units, like dollars and ounces.
Right. If they are the same, you just have a ratio. Apples and dollars. Got it.
Step 2, write the rate as a fraction, numerator over denominator, and explicitly label those units.
And the sources emphasize that labeling the units is not optional busy work, right?
Not at all. It is the single most important error prevention habit you can develop, because the units tell you whether you set up the division correctly.
Okay, what's step 3?
Step 3 is to reduce to a unit rate by dividing, so the denominator becomes 1. If you have 180 miles in 3 hours, you divide 180 by 3, you get 60 miles per 1 hour.
So that single act of division is the entire computational heart of finding a unit rate.
Exactly. And then step 4 is to use that unit rate to scale or compare. Once you have a per 1 value, you can multiply it or divide it to find anything else, or compare it to another product.
Which exposes exactly the traps retailers set.
Oh, they definitely set traps. Manufacturers play on our cognitive assumptions rather than our math skills.
So what does this all mean? Let's use that example from the sources. Say I'm in the cereal aisle, looking at a 12-ounce box for $3.60.
Okay.
If I divide that in my head, let's see, 360 divided by 12. That's exactly 30 cents an ounce. But sitting right next to it is the family size. An 18-ounce box for $5.94.
And what would you normally do?
Normal, I would just grab the big box. We have this universal instinct that buying in bulk saves money. But if I actually do the math on that large box, okay, 5.94 divided by 18. Wait, that comes out to 33 cents an ounce.
Yes, it does.
It means the larger package is actually more expensive per ounce.
You are paying 3 cents more for every single ounce just for the privilege of buying a bigger cardboard box.
That violates every instinct I have as a shopper.
This directly addresses a major psychological hurdle, which researchers call misconception 3. It's the assumption that a bigger package always equals a better price.
And manufacturers know this, don't they?
Oh, they bank on it. They bank on the fact that shoppers will see a family-size label and just assume it's a better deal without taking 10 seconds to do the division.
Wow.
This is a phenomenon deeply tied to shrinkflation and what's known in consumer economics as the large size penalty. It is absolute proof of why step 2, labeling your units, and step 3, doing the division yourself, are entirely non-negotiable if you want to protect your wallet.
Okay, being tricked out of 3 cents an ounce is annoying, I'll admit that. But if you take the same math and step into a hospital ward, failing to properly compute a rate isn't just about losing pocket change.
No, it can literally cost a life.
And this is exactly why unit rates are tested so heavily on the TEAS and HESI nursing entrance exams.
In the medical field, rates govern almost everything you do. Even everyday vital signs are unit rates. Heart rate is beats per minute. Respiratory rate is breaths per minute.
So counting a pulse is just a rate calculation.
Exactly. When a nurse counts a patient's pulse for 15 seconds and then multiplies that number by 4 to get the full minute, they're simply scaling a unit rate. They're using the exact same mathematical logic as converting a 3-hour drive into a miles per hour speed.
But the 5E infusion math is where the stakes feel so much higher to me. There's an example in the prep books that really caught my eye. A physician orders 1,000 milliliters of normal saline to infuse over 8 hours via an IV pump.
And the pump delivers in milliliters per hour.
Right.
That is a standard, straightforward calculation. You simply take the total volume and divide by the time. 1,000 milliliters divided by 8 hours equals 125 milliliters per hour.
That is exactly the reduced to a denominator of one operation we just talked about.
It is.
But then the sources introduce the gravity-fed IV complication. And this is what apparently trips up almost every new nursing student. A gravity-fed IV tubing setup does not deliver fluid in nice measurable milliliters.
No, it doesn't.
It delivers fluid in drops. And the abbreviation for drops is GTT, which I learned today. But here's what astonishes me. The numeric value of 125 milliliters per hour is entirely meaningless if you don't know the physical size of the plastic tubing.
That's the catch. You have standard macro drip tubing that might deliver 10, 15, or 20 drops per milliliter. Then you have micro drip tubing that delivers a tiny 60 drops per milliliter.
And you just have to know this.
Well, this drop factor is printed on the packaging. It is not something a nurse can just guess or eyeball.
So if you need to convert that 125 milliliters per hour into a drip rate using, let's say, 15 drop per milliliter tubing, how do you actually do that? How do nursing students keep all these changing units straight under pressure?
That's where dimensional analysis comes in.
I saw that in the prep books, but how does it actually work conceptually?
Think of dimensional analysis as a translation machine. Just like you would use an exchange rate to translate American dollars into European euros, you use the tubing's drop factor to translate the language of milliliters into the language of drops.
Okay, I think I follow.
You set it up as a chain of fractions so the units cancel each other out.
Walk me through that translation in steps.
First, if you have 125 milliliters flowing in an hour, and you know each one of those individual milliliters is made up of 15 drops, you multiply those two numbers together.
Which tells you what?
This tells you how many total drops are falling in that entire hour.
So 125 times 15, that is going to be a massive number of drops.
Exactly. But once you have that massive number, you don't want to stand by the bed for an hour counting them. You need to know what falls in a single minute.
Right, obvious.
So you just divide that big number by 60, since there are 60 minutes in an hour. By setting it up as fractions, the milliliter words and the hour words cancel each other out, leaving you only speaking in the new language of drops per minute.
That's incredibly elegant.
In this specific case, it comes out to approximately 31 drops per minute.
So the exact same physical reality, 125 milliliters of fluid entering the body over an hour, produces a completely different countable number on the machine depending on the plastic tubing being used.
It is a vivid, concrete illustration of why a rate's numeric value means nothing without its units attached.
And the stakes for getting that translation wrong are terrifying. The sources spend a lot of time on the danger of misplaced decimals in these calculations.
Decimal point errors in medication dosing are a sobering reality. A misplaced decimal can produce a 10 times or even 100 times overdose of a critical drug like insulin or a sedative.
Which is horrifying.
Yeah, it is. The Institute for Safe Medication Practices, the ISMP, has published strict guidelines to prevent this. They mandate the use of leading zeros.
Mean what exactly?
Meaning you must write 0.5 milligrams instead of just 0.5 milligrams. If a doctor scribbles just 0.5 and the dot is faint, a nurse rushing through a shift could easily misread it as a full 5 milligrams.
A tenfold overdose just from a faint dot on a page. That's chilling.
They also ban trailing zeros, meaning you write 5 milligrams, never 5.0 milligrams, because that could easily be misread as 50 milligrams.
Wow.
These conventions exist strictly because small notational slips in rate calculations have killed patients. Nursing programs drill this arithmetic relentlessly for a reason.
Okay, so the core math is basically just dividing a numerator by a denominator. Why do adults, nursing students, and everyday consumers still struggle with it so much?
It's a great question.
Here's where it gets really interesting. It's not just about doing the division. It's about how our brains interpret the results. Take fuel economy, for example.
Right.
Miles per gallon is a unit rate, but it is an inverted one compared to how much of Europe measures fuel, which is liters per 100 kilometers.
Rate inversion is a fascinating cognitive trap.
Right. If you upgrade from an older car that gets 40 miles per gallon to a newer one that gets 50 miles per gallon, a naive, linear reading of the numbers makes it feel like a huge leap.
It feels like a massive improvement.
Yeah, going from 40 to 50 feels like a massive 25% improvement in efficiency. But when you actually do the math over, say, a 1,000-mile road trip, the 40 mpg car uses 25 gallons of gas.
A newer one.
The 50 mpg car uses 20 gallons. You only saved 5 gallons of gas over 1,000 miles. It's like trying to compare the speed of two runners by measuring how many seconds it takes them to run a single foot rather than how many feet they run in a single second. It completely flips your intuition upside down.
That is an excellent analogy. If we connect this to the bigger picture, it shows that which quantity you place in the numerator versus the denominator drastically changes how a difference feels to the human brain, even when the underlying math is perfectly correct.
It's a mental trick.
It is. And this cognitive difficulty is exactly why the famous developmental psychologist Jean Piaget argued that ratio and rate reasoning is a hallmark of the formal operational stage of cognitive development.
Meaning it's a high-level cognitive skill, not just rote memorization.
Exactly. Piaget claimed this level of proportional reasoning isn't typically mastered until adolescence. Younger children might be able to add and subtract in what he called the concrete operational stage, but rates require multiplicative thinking.
You have to hold two moving variables in your head at once.
You do. You have to understand how they interact as a single unified concept. Some modern critiques suggest even many adults struggle to fully master this.
Which makes sense.
That is why rate and proportion problems are disproportionately hard for adult learners returning to math for nursing entrance exams. It is a complex cognitive leap.
And it also ties into misconception 5 from our sources, which is the mistake of trying to compare rates with mismatched units. People try to directly compare milliliters per hour to drops per minute without doing that translation step we talked about. It just doesn't work.
It doesn't work at all. And this brings us back to the great educational debate we touched on earlier regarding the Common Core.
Right, the ratio versus rate debate.
Do we strictly separate ratios and rates to prevent these exact cognitive errors in STEM and healthcare? Or, as some critics argue, does that strict separation just add confusing vocabulary overhead to what is essentially just continuous multiplicative comparison?
That's a call.
Defenders of the strict separation point right back to the hospital ward. Conflating a ratio and a rate is exactly what leads to forgetting units, which leads to medical errors.
So we've traveled from the foundations of physics with Galileo to the grocery store aisle to dodge the large-size penalty, into the hospital ward for life-saving 5e math, and deep into the cognitive psychology of how our brains process these numbers.
We've covered a lot of ground.
We really have. Let's bring all these threads together for you. Based on everything in the source material, here are the 5 key exam-style takeaways you need to remember.
Number 1, a rate compares two different units and keeps both of them in the answer. A ratio compares the same unit and keeps neither.
Number 2, finding a unit rate is just dividing the numerator by the denominator until the denominator is exactly 1. That single act of division is the whole technique.
Number 3, units must match before you can compare them or convert them. Milliliters per hour and drops per minute are not interchangeable without a conversion step.
Number 4, an average rate can hide moment-to-moment variation. A constant rate and an average rate are not making the same guarantee about reality.
And number 5, bigger is not automatically cheaper per unit. Packaging size is designed to be judged by eye, not by unit price. Always do the math yourself.
We've talked about how rates govern space, time, money, and medicine. But I want to leave you with a final thought to ponder. Think about the invisible algorithms running your digital life right now.
Oh, that's an interesting angle.
Your internet bandwidth is measured in megabits per second. Your social media clout is judged by engagement rates, likes per view, comments per post. You are constantly being measured, quantified, and monetized in per unit values.
It's the unit rate of the modern era.
Exactly. So the next time you are scrolling on your phone, ask yourself, what is the hidden unit rate defining my attention right now, and who is doing the math? It might just be the modern equivalent of that Trix cereal box, only this time, you are the product. Thanks for joining us on this deep dive. Keep questioning the numbers, and we'll see you next time.